So I've gotten a request to do the discussion board for today's live stream. So what I'm going to do is I'm going to try to switch it to the browser. This way it's a bit easier to see what I'm talking about. So the discussion board this week and the discussion board I'm referring to here is the discussion board for Organic 1. If we switch it over to the discussion board, you're given Nmr data, C13, and the 1H Nmr, and then you're given the information in tables below. And the information table below is just because it's not always clear, especially with these simulated spectra, what's really going on. So I've opened these up into other windows. So I've got the 1H Nmr spectrum, carbon 13 Nmr spectra, the 1H Nmr spectra, and then I've got a table summarizing that information. So this is the same information on both. It's just it helps clarify what the information is. So for the carbon 13, we've got 5 peaks, 1, 2, 3, 4, 5, with relative areas of 1, 1, 1, 3, and 1. And what this relative area means is that if we look at whatever molecule we're referring to, this is the ratio they appear in. For the 1H Nmr, same thing. We've got 4 peaks now instead of 5, and they appear in a 2 to 3 to 2 to 9 ratio. Now, to kind of help you out here, I've also given you a copy of the molecule itself as well. So the molecule is labeled here A, and it tells you it's pointing to all 3 of these, and what it means is that these 3 carbons are equivalent. And B here is going to have its own chemical shift, C is going to have its own chemical shift, D is going to have its own chemical shift, and E is going to have its own chemical shift. So how are you going to know if something is considered unique? Well, you're going to have to, this is kind of why we covered the symmetry first, is you need to look at it and see, do the carbons look exactly to the same, or are they bonded to the same things? And I mean within 2 or 3 carbons, are they bonded to the same thing? So if we look at this D carbon, it's bound to a methyl and then a CH2. That's not the same thing as the C carbon, which is bound to a CH2, and then a carbon, which is bound to 3 other carbons. So that's why these C and Ds would have they would have their own chemical shift. They'd have their own point in the spectrum. Now, good for you, McGraw-Hill. Now, you're going to eventually figure out how to, part of the reason you're getting this problem is to kind of help you see how to identify it. But what we expect to see here are 5 peaks because we have 5 carbons, A, B, C, D, and E. Now, what about the ratios? Well, we got 1 carbon that looks like E, 1 D, 1 C, 1 B, 3 A's. So the challenge with this one is going to be figuring out which carbon corresponds to which one. The reason being that they're all going to have very similar chemical shifts. So the A is easy to figure out. We have 3 carbons like this, so it's going to be the one that has a 3 to 1 ratio. So if I switch to the carbon 13 data, we have peak 4. So peak 4, let me get out a sheet of paper so I can, good for you. Get out a sheet of paper so this way you can see a little bit more easily. So peak 4 is the one that has 3 carbons associated, so we can automatically tweeze out that peak 4 is carbon A. So I'm going to keep a running tally here on my little yellow sheet. So here I've made a list of the carbons in the image, A, B, C, D, E, and the carbon 1H and the carbon 13. Now, one of these carbons is not going to have a proton associated with it. Because if we look at carbon B, it's already got 4 bonds in it, which implies that there's no hydrogen. So B here is not going to have a 1H Nmr spectrum associated with it. So now we just need to figure out what B, C, D, and E are. So how do we figure that out? Well, we look at shielding. And the more hydrogens we have around carbon, the more shielded it's going to be. So when we say shielded, the more towards negative its chemical shift is going to be. So if we look at E, E's got the most hydrogen, so we expect this to be the most shielded. So it's going to have the chemical shift furthest to the right, so that's going to be number 5. If we look at the one that's got the most carbons around, that's going to be carbon B. So carbon B is going to have the highest chemical shift with an area of 1, so it's going to be peak 1. Now, as far as C and D go, it's going to follow the same line of reasoning. I guess I could flip you over there to the desktop. So if we go to carbons C and D, these get progressively more D-shielded because they're surrounded by carbons that have less and less hydrogens. So this D is around a carbon that has 3 hydrogens, this one only has 2. So D is going to be the second most shielded, and carbon's around one that has two hydrogens and no hydrogens, so it's going to be more D-shielded than D. So if we kick over to this spectrum, we've already used up peak 4 and peak 5. So, because peak 4 was carbon groups A and peak 5 was carbon group E, and B we know is peak 1, so this leaves us with peak 2 and peak 3, and the more shielded there is going to be 3, so D is going to be associated with the third peak, and C is going to be associated with the second peak. So again, let me bring that up for you. So again, how did I arrive at this line of reasoning? Well, the more hydrogens we have around the carbon, the more shielded it's going to be because it's going to have a more negative charge around it. We're going to look at the oxidation states. So again, we figured out that carbon A was number 4 because it's got an area of 3, and there's only one where we got 3 types of the same carbon. E we figured out was peak 5 because E has the most shielding. It's got the most hydrogens around it, so that would be peak 5. The way we tweezed out peak B is that it's going to be the most D-shielded. So that's going to be peak 1, which is what I have. And these get progressively more shielded, 2 and 3. So each one of these has more and more hydrogens on itself as well as the carbons around it. So now we worked out the carbon 13. How about the 1H Nmr? Well, to do this, let's do the same thing. Let's start figuring out the easy ones. So if I go back to the molecule itself, and again, this is why you typically don't take a spectrum and go backwards. You typically have it guess and go forward. We've got the terms here: multiplicity, doublet of triplets, triplet, singlet, and triplet. So a singlet will correspond to a peak that has, actually I think this might be mislabeled. Maybe I'll update it on the discussion board. So I will correct this. This actually should be a singlet for number 4. So first of all, look at the relative areas. That should be the big tip off. So all these A's have the same hydrogens, so we're looking for an area of 3, 6, 9 hydrogens, and that's why this is mislabeled, so I will correct that on the slides. Peak 4 here is going to correspond to your A hydrogens, and that's because we have an area of 9. Now, we've got 2 other carbons. We got 3 other hydrogen-bearing carbons. We've got E, which has 3, D, which has 2, and C, which has 2. So this is where we're going to work with the J coupling. Now, you're better to go with hydrogens. We'll start with hydrogens that only have hydrogens on the nearest neighbor. So if we look at E, it should be we've got 2 carbons here, so it should be a triplet. And if we look at the spectrum, we've got a triplet here at 0.872. So peak 2 here, and actually the 3 here should be a triplet as well. Well, first of all, it's the only one with 3 hydrogens. So yeah, I'm sorry. Getting a little rusty on my 1H Nmr. It has an area of 3, and this is the only carbon we see that has just 3 hydrogens on it. It's C and D that have the 2. So since this has an area of 3, it tells us that carbon E, or hydrogens on atom E, correspond to the second peak. So I'll bring back up the summary really quick for you. Come on. So we got A being associated with the 4th peak because it's got an area 9, E being associated with the 2nd peak because it's got an area of 3. How do we figure out C and D? Because B is not going to have a chemical shift for hydrogen because it doesn't contain any hydrogens. Well, in this case, we're just going to look at the multiplicity. So for peak 1, we have a doublet of triplets. This implies that we have a carbon that is adjacent to other hydrogens. So it's got hydrogens on both sides. So we only have one set of hydrogens that has 2 different types of carbons on it. So we only have one atom that has 2 different types of neighboring hydrogens. So atom D here has the hydrogens on E and the hydrogens on C, which are different bonding environments. So we expect a multiplet for this one. And the only one that has a multiplet is peak 1. So carbon D, atom, that functional group D, is going to have that chemical shift at 1.254. It also has an area of 2, which is what we expect. By process of elimination, the only one we have left is number 3. But the reason why that we know, if I had labeled it correctly, that number 3 is the other one, is the only one with 2 hydrogens, and also this should say triplet here. So this is how you go through and analyze the 1H in the carbon-13 NMR to figure out what corresponds to which. Now, the carbon is quite frankly the easiest to understand because it's very straightforward. You're going to have one peak for each unique functional group. So in this case, these 3 are the same because they are all methyl groups attached to the same carbon. This E group is by itself because it's a methyl group, but it's not attached to a carbon surrounded by 4 other carbons. It's attached to a carbon that's attached to another carbon and 2 hydrogens, which is why it's going to have its own unique chemical shift. B is going to have its own unique chemical shift because it's bound to 4 carbons. C is going to have its own unique chemical shift because it's bound to a carbon with 2 hydrogens and a carbon with no hydrogens. And D is going to have its own unique chemical shift because it's the only one bound to a carbon with 2 hydrogens and a carbon with 3 hydrogens. So we look at the relative areas for the carbons to figure out which one corresponds to which. Hydrogens, we're going to use both the area. So in this case, we have 9 and 3 and 2 and 2. So we have 9, 3, 2, and 2. So the 3 and the 9 are easy to figure out by the relative areas. And then the 2 and the 2 we're going to figure out by the splitting pattern. But again, I need to update this discussion board because that's not actually correct. So everything else here is correct, but that's not correct. So this is how you answer the discussion board question based on the spectrum pick which atom, A, B, C, D, E, or which functional group corresponds to the 1H in carbon-13 NMR. So unless I see questions up on the discussion board, I'm just going to mute the volume for right now. I'm going to try to update this discussion board right now while we're still here. But please feel free to ask any questions. Otherwise, I'm just going to get to grading after I update the just got a question up. What was B and C for the 1H? B did not have a peak associated with it. For C, it's going to be peak 3. And 3 is going to make a little bit more sense if you give me just a minute to update the table. But the reason why 3 ends up being the C atom or the C functional group is that it doesn't have a multiplet. So its 1H NMR isn't broken, it isn't like a doublet of triplets. So since, switch the view for you really quick. If you look at the C carbon, there's no hydrogens on B, and D has 2, so we expect this to be a triplet. And you can see where I flipped the singlet and the triplet in the table. So C here is going to be a triplet because it sees these 2. D is going to be actually a triplet of quartet, so that needs to be updated in the table as well. But that's where that comes from. That's how we can resolve C and D. They both have 2 hydrogens on them, so we do get, open this new tab. We do get this 2 and 2. So we know 1 and 3 had to correspond to C and D. The question is which is which. Because we expect D, which has vicinal hydrogens of both the C and the E carbons, we expect that to be a multiplet, which is what we see here. So we know 1 corresponds to D, and we expect 3 to be a triplet. Again, the singlet and triplet are flipped. So that's how we know that peak corresponds to carbon C. Yeah, it's going to make a little bit more sense when I correct the table in like 5 more minutes. Unfortunately, I'm here and not at home where I have all my files that have all this in it. Yeah, you're welcome. So on the lab on Tuesday, we never had a lab. We went over this in the lab, but how were we able to determine which solid was which molecule without being able to do the melting point of the lab? So the way we do that is by looking at the reactivity of the molecules. So let me grab another sheet of paper. And I'll draw the three molecules out so we can talk about them. So we have three molecules. The first is benzoic acid. Second is naphthol. Yes, I'm about to put them up to the monitor. And the other is para-dimethoxybenzene. So these three molecules here, benzoic acid, naphthol, and para-dimethoxybenzene. Now, we're going to use process of elimination to figure out where they're going to go because we have solutions A, B, and C. C is the organic layer. Well, one of these doesn't react. Two of these act as acids or bases. The third does not do anything at all. So the para-dimethoxybenzene does not react with any of the reagents. It stays as a covalent compound. So your para-dimethoxybenzene here is going to end up in your organic phase when you're done. So we know the para-dimethoxybenzene ended up whatever ended up being the organic phase when we were done. Benzoic acid, as the name implies, is an acid. So this is going to react with whatever base you had. So the pKa of benzoic acid is less than 7, which means it's a better acid than water. So whatever aqueous phase you added that had a strong base in it, that's going to contain the benzoic acid. As for the naphthol, process of elimination, it's got to be the solution. But if you want confirmation on what it is, it has a pKa greater than 7, which means it's a better base than water. So again, it's going to react, but it's going to react in the solution that's not basic. And you might get a little misled when you look at the other aqueous solution, but what you added was actually a weak acid. Not a great acid, but it is a weak acid. So that's how you determine which one ended up in which phase based in the lab, by the reactions that you expect to happen. Two of these end up doing acid-base reactions, so they fall in the aqueous. The third doesn't, and that gets into the organic layer. The other two, you'll know which one they popped off based on what was in the water that you used to separate it out. So since 1.5 molar acid is a strong base, then that will be what reacts to solution A since it is an acid. Not solution A, it reacts with the benzoic acid. So the benzoic acid is going to fall out in the solution where you added the sodium hydroxide solution. Now you're going to check the lab manual to see which one was which. Yes, sodium hydroxide is definitely a strong base. It looks like the discussion board shifts tables are correct now. Yeah, I flipped the labels there at the bottom. Well, I mean, yeah, you should trust your recall. That's why I made you memorize that list of strong acids, strong bases, so you would like know. Like it still goes on, right? Like organic, even though you're organic, some of the stuff you learned in Chem 1, Chem 2 does still follow through. So questions we haven't covered on the study packets yet would be the ones about NMR and characterization. So we are just now getting to those. Let me bring up the packets really quick. So for the packets, we've done basic definitions, we've done line bond drawings, identifying functional groups. Hybridization, you do need to know, this is kind of a refresh from Chem 1, Chem 2. I'm not going to do a discussion board on it, but it is going to be on the exam. Electrostatic potential maps we haven't covered yet, but we will get to those. Optical activity we haven't gotten to yet. Newman projections we've definitely done. Fisher projections we've done. Energy of isomers we're going to start. We're doing this between now and the exam, and that kind of breaks. You should be able to do this in terms of what's eclipse versus gauche and anti. Confirmations you should know how to do. Chiral centers you know, and androstat centers you know, naming chiral centers you know, and then the characterization. So the big ones are the characterizations, the ESP, electrostatic potential maps, and the optical activity. Those we have not done yet, but that's what we're covering now between now and the exam. So you're about halfway done with this study packet, which makes sense because you're about halfway to the exam date. You're welcome. Question you just got asked, will I read rough drafts in advance? Yes. So for any lab report, if you give me about 2 or 3 days lead time, I'll look over your lab report. I won't give you a grade, but I will definitely give you feedback, particularly in the major issues I see. So yes, you're always free to send your lab report in advance. Then that said, it's one per student. So if you're the type of students like, I'll send them a whole bunch of drafts, that's not going to happen. I'm also pretty clever. So if you try to do I just want to ask about this one thing, that's going to count towards your revision. So you may ask me general questions about the lab report, but if you want me to look over a specific section, that needs to be done. That's going to count towards your revision. So don't send me it piecemeal trying to get me to revise it a whole bunch of times. I'm only going to look over your specific work once. Got a question. If you send the lab in wrong with the wrong number of sig figs, usually a point or two off for each sig fig, unless you're giving me like calculator output. That says you're doing pretty trivial calculations for organic. So probably at most 1 to 2 points per sig fig. All right, you're welcome. Please feel free to ask any other questions you have. So the question got asked, can we review hybridization on pages 10 and 11 of the packet? So let me bring that over to the desktop. So with hybridization in Chem 1, when you do the full table, you're based off the AY geometry. So if you're taught AXE for figuring out the molecular geometry, the AY is just some number of X's and E groups. Now, honestly, with organic chemistry, it's just a lot easier to memorize because there's only a handful of combinations. So if we have carbon with 4 bonds, it's sp3 hybridized. If it has 3 periphery atoms, it's sp2 hybridized. If it has 2 periphery atoms, then it is sp hybridized. Exceptions to this are lone pairs. So if we have a lone pair on the carbon, we're just going to treat that as an additional bond. Nitrogen, if we have 3 atoms around it, it's sp3 hybridized because that lone pair on it's going to give us make it look like a 4th bond. If we have 2 groups around the nitrogen, it's sp2 hybridized. If we have 1 atom bound to it, it's sp hybridized. For oxygen, because there are 2 lone pairs, if we have 2 things bonded to oxygen, it's sp3 hybridized. If we just have 1 thing bonded to it, it's going to be sp2 hybridized. So for the example here where we've got a carbon double bond to this carbon and we have this carbon here that has 4 bonds, this carbon is sp3 hybridized. This carbon is sp2 because it's only got 3 other atoms around it, and this carbon is sp2. So we would say the hybridization of the left carbon, the center carbon, and the hybridization of the left carbon and center carbon are sp2. Hybridization of this carbon is sp3. As far as the bond is defined as the orbitals that are used to make the first bond. So carbon here, hydrogen's going to use its 1s, so the bond between carbon and hydrogen is an s to a carbon sp3. The bond between this center carbon and the right carbon, well, we have an sp3 carbon bound to an sp2 carbon. So the bond is an sp2 to an sp3. For the 2 carbons that are double bound, these are both sp2 carbons, so we would say the bond is an sp2 to an sp2. And for this carbon hydrogen here, it's an sp2 carbon bound to an s hydrogen s, so it's sp2 to an s. And that's really kind of how the rest of these are going to work. For this example here with HCN, carbon is sp hybridized, it only has 2 things around it. Nitrogen is sp hybridized because it's got the lone pair and then the carbon to give us 2 for sp. So the bond between the nitrogen is a nitrogen sp to a carbon sp. For the carbon hydrogen, it is a carbon sp to a hydrogen s. So that's how those problems work, and that's why there really aren't that many on there. It was hard to come up with examples that didn't seem horribly repetitive. You're welcome. Hybridization isn't, for organic, it's a lot easier than what you learned in Chem 1 and Chem 2 because we're only dealing with the top right part of the periodic table. And we're not dealing with a lot of weird octet exceptions. Well, I could, but well, I guess you'll be in lab Tuesday. Yeah, I'll try to remember. So we don't have a live stream Tuesday. Oh, that makes sense. Okay, in lab. Well, we can do that. The fiddle sounds less and less like the death of music every day, but still a long ways from it. I think the big issue I'm having right now is not getting to the notes, but rather it's North Carolina and the resin is really getting sticky in the humidity. So I'm constantly having to put resin on the bow, play it, then pull the resin back off. And I kind of came to this conclusion because I was noticing like the middle of my playing was getting like to the point that the bow was passing the strings very easily. But for some odd reason towards the end, like this bow was just like grinding across the strings. And that's when I noticed my fingers were getting really tacky with the resin dust that was getting onto it. So I think what happens is that when I first start playing it, I'm just inherently knocking off the old resin. New resin gets onto it, and the new resin starts getting moisture on it, and that starts creating that scratching sound. But I'm to the point now, the second and third strings, I'm pretty consistent about where I'm hitting the notes. So I can consistently do the first three fingers. There's definitely a little bit of fun with the F sharp. Like, I'm still kind of learning where that note is, but I mean, I do cheat. I'm going to play it after the live stream today through my break before Orgo 2. I'm still cheating. I got all the notes written down on the fiddle. But it is actually not as bad as I thought it was going to be. So, real question about the RS configuration, how you determine them without a model. I have a time visioning the atoms on the front versus back and how that changes the R and the S. So this can be done using a Fisher projection. I'm not a huge advocate of it. And I'm not a huge advocate of it because it's basically reinforcing a bad habit on a Fisher projection. So I'm going to draw a fake Fisher projection. And I'm going to just write the priority of the groups, 1, 2, 3, 4. So if I've got my groups 1, 2, 3, 4, and I want to figure out if this is R or the S, I'm going to rotate it so that the one group is back. And what that ends up doing is causing whatever's opposite the one to go to that side. So the way we would draw this to figure out the R and the S is we would move the 2 over to where the 1 is, and we would just omit the 1. So this is what you would end up getting. So if we start with 1, 2, 3, 4, and we rotate it so the 1 is in the back, it effectively looks like this 2, 3, 4 that I've got on, what side is that to you? Left side. So now I can do it. I've got 2, 3, 4. This is clockwise, so it's R. The reason I don't like teaching it this way is that you're kind of cheating with the Fisher projection, and you can get into a bad habit of thinking that now that I've done it for this carbon, I can move on to the next one. But if you don't have a modeling kit, this is what you do. So we grab another one so we can work a different example. So let's say I have these two examples. The top one I have 1, 2, 4, 3, and then one beneath it I've got the 1, 2, 3, 4. So to figure out if it's R or S. Oh, I'm sorry, I flipped the priorities. So, sorry. Disregard what I said with the earlier example. We'll work on these examples. So to figure out if these two examples are R or S, the lowest priority here is 4. So what we're going to do is we're going to swap the 4 whatever's opposite in this line bond drawing, and then we're going to erase the 4. And this is effectively what happens when you rotate that carbon in order to put the lowest priority carbon in the back. So when I rotate it, this is effectively what my structure looks like. So I take it from take whatever's opposite that 4 and rotate it over. So in this case, my 1 and my 4 are opposites. So now my highest priority ends up on the opposite side, and now I can figure out the R and the S. If I look at the 1, 2, 3, that's a clockwise motion, so this would be R. For the one beneath it, my lowest priority is up, and my lowest priority, number 4, is up. So what I'm going to do is I'm going to switch the 2 with its position. And the 4 is going to disappear behind my drawing. And when I do this, I get a structure that looks like this. And so now all I got to do, it goes 1, 2, 3. That's clockwise. This is also going to be an R conformation. So this is how you would manipulate, if you didn't have a modeling kit and weren't able to turn it in real space, this is what you do. You would take whatever is opposite the lowest priority group and replace it, and then erase the lowest priority group. And that's effectively what you're doing when you rotate the model, is that when you rotate it, you're rotating across. So this one where we got the 4 up, you're rotating across this 1, 3 line. For the one above it, we're rotating across the 2, 3 lines. So they're going to swap places, and then when you rotate it, that lower priority group disappears behind it. So hopefully that helps, but that's how you would figure it out if you don't have a modeling kit. Glad that helped. I mean, again, the reason I don't like teaching it that way is that students will make that rotation in their diagram and then forget to undo it when they move to the next chiral center, and it gets really confusing because you've got a Fisher projection that you've manipulated to get the answer to, and now you need to go back to your old Fisher projection. That's what I recommend. So draw your Fisher projection and keep your correct Fisher projection, and then every time you want to go to R and S, do it off to the side as a different one. So you still got your initial Fisher projection, but when you do that RS determination, you're not tempted to try and reuse it for the next problem. Okay, so if your NMR only has singlets in it, that means that you never have two adjacent carbons that both have hydrogens. It's always a carbon with hydrogen, then a carbon that doesn't have any, then a carbon with hydrogen, the carbon doesn't have any. Now, you can estimate, yeah. Now, also, if it's a single peak, it means that there's a lot of symmetry with this molecule. Does it give you the area, or does it give you an area other than one, or does it just say a singlet? I guess it makes sense. If you only have a single peak, it's going to be an area 10, so it doesn't matter. Are you sure it's H10? Just check that number really quick. So 1.5 just means it's a methyl, or it's carbon possibly with double bonds, but you're probably looking at hydrogens bound to a carbon that's single bound to something else. That's why I'm kind of wondering if that's really a H10 or if it's supposed to be some multiple of 3. Cyclopentane. Oh, because they're all the same. Well, actually no. Cyclopentane. Hold on. They're all equivalent. There's only one functional group in that molecule, so you should only have one chemical shift, and since they're all the same, they don't J-couple. I mean, it makes sense to say that you would only have one peak because there are no unique functional groups within that molecule. They're all CH2s. But that makes sense. There is no CH2 group within that cyclopentane that looks any different than the others. But yeah, that's the answer. If you're That's the answer. It is cyclopentane. They make sense. There's only one carbon in there, so you only have one chemical shift. Alright, so it's 1 o'clock. I need to take off so I can start prepping for my Orgo 2 lab. Again, if you have questions, we got a live stream tomorrow at 2:30. If you're not able to make the live streams, please send me an email and I will try to answer your questions at the start of the live stream. So I will see you all, if not on live stream tomorrow, then sometime next week.